You know, in machine learning, we work with these beautiful, elegant mathematical formulas that, on paper, look absolutely perfect. But then you try to run them on an actual computer, and things can go sideways. It turns out that leap from pure math to practical code, well, it's riddled with hidden dangers.
So why? Why do these perfectly correct equations sometimes just completely fall apart on our machines? It really all boils down to this fundamental clash between the infinite, flawless world of mathematics and the very finite, very limited world inside a computer.
Okay, let's really get into this. In the world of pure math, a number like pi can have infinite decimal places. No problem. But on a computer, you only have a certain number of bits to store that number. It's finite. So the computer has to make approximations, and these tiny, tiny little rounding errors can build on each other and cascade into total system failure.
And to see just how bad this can get, let's look at our first case study, the Softmax function. Now, this thing is a real workhorse in deep learning. It's used everywhere for classification tasks. But this everyday, super common function has a critical vulnerability. So here's the formula. Basically, its job is to take a bunch of raw scores, we call them logits, and kind of squash them into a nice clean set of probabilities that all add up to 1. So if you're trying to figure out if a picture is a cat, a dog, or a bird, Softmax is what gives you the probability for each one. Seems simple enough, right?
Well, here's the problem. See that exponx part? If one of your input values, let's call it c, is a really big positive number, the exponc c calculation just explodes. The number gets so huge that the computer literally can't represent it and just throws up its hands and calls it infinity. And that starts a chain reaction. The denominator becomes infinity, and you end up trying to calculate infinity divided by infinity. The result? Nan, not a number. Your program crashes.
And what's wild is that it fails in the exact opposite direction too. If your input values are really large negative numbers, exp in C becomes so incredibly tiny that it underflows, meaning the computer just rounds it all the way down to 0. If all your numbers do that, your entire denominator becomes 0. And you know what happens when you try to divide by 0. Boom, another crash.
So what do we do? Do we need some crazy new mathematical theory? Nope. The solution is actually a really simple, super practical, and just elegant engineering fix. And this is what's so cool about it. Mathematically, the answer we get doesn't change one bit. We're not changing the math. All we're doing is using a little bit of algebra to rewrite the formula in a way that our finite computers can actually handle without breaking. So what is this magic trick? It's almost shockingly simple. You take your input vector, you find the biggest number in it, and you subtract that number from every single element in the vector. That's it. That one little step makes the whole thing numerically stable.
And hey, don't just take my word for it. The deep learning book itself points this out, saying that simple algebra shows the final answer doesn't change. It's the same formula, analytically speaking, but for a computer, it's the difference between working and crashing.
So how does this one little trick solve both of our problems at once? Well, first, the overflow. By subtracting the max value from everything, the largest number you'll ever feed into that xp function is 0. And xp of 0 is just 1. A perfectly safe, manageable number. No more explosions. And for underflow, since we know the biggest number is now 0, we're guaranteed to have at least one term in that denominator sum that equals 1. This means the total sum can never, ever be 0. No more division by 0 errors. Problem solved.
Okay, so that's how we stabilize a single function. But these kinds of numerical gremlins pop up on a much grander scale, especially when we're trying to train an entire model. This gets us into the whole challenge of optimization, which is kind of like trying to find the absolute lowest point in a huge, foggy, high-dimensional mountain range.
Now, our main tool for navigating this terrain is something called the gradient. You can think of the gradient as a magical compass that always points in the direction of the steepest uphill slope. So if we want to get to the bottom of the valley, we just take a small step in the exact opposite direction. We go downhill.
But here's the catch. What happens when the ground becomes perfectly flat? The gradient becomes 0. Our compass just stops spinning. Now, we might think, great, we've made it, we're at the bottom. But in these incredibly complex, high-dimensional landscapes, that's almost never the case. Chances are we've just landed on something called a saddle point. The name is pretty literal. Think of a horse's saddle. If you move along the horse's spine, you're at the bottom of a curve. But if you move across it from side to side, you're at the very top of a curve. The spot right in the middle is totally flat, but it's definitely not the lowest point you can get to.
So our little gradient compass is now useless. It can't tell us which way to go.
To get out of this trap, we need a much more sophisticated tool. We need something that tells us about the curvature of the landscape. And that tool is called the Hessian Matrix.
Now, the formal definition involves second-order partial derivatives, but let's just stick with our analogy. If the gradient is a simple compass that points one way, the Hessian is a full-blown topographical map. It describes the entire shape, the curvature of the surface, right where you're standing.
And how do we read this map? It's all about something called eigenvalues. If all the eigenvalues of the Hessian are positive, it means everything is curving up. We're at the bottom of a bowl, a real local minimum. Awesome. If they're all negative, we're on top of a hill. But if we get a mix of positive and negative values, that's the dead giveaway for a saddle point. From a systems engineering view, the ratio between the largest and smallest eigenvalue gives us what's called the condition number. A huge condition number tells us we're in a really long, narrow, steep ravine, an ill-conditioned problem that is an absolute nightmare for our optimizer to navigate.
The classic textbook example of a function that has this saddle point shape is this one right here. F of x is equal to x1 squared minus x2 squared. It's basically the perfect mathematical recipe for that Pringle chip shape we were talking about.
And this chart just spells it out visually. If you move along that first dimension, the x1 axis, the curvature is positive. It curves up like a smile. But if you move along the second dimension, the x2 axis, the curvature is negative. It curves down like a frown. That mix of up and down curvature is the signature of a saddle point.
All right, let's zoom out and pull all this together. We've looked at two very different numerical problems and the clever engineering that solves them. So what's the big picture lesson here for anyone trying to build real-world deep learning systems?
Well, it really boils down to a few core engineering principles. First, you have to anticipate and respect the physical limits of your hardware. Second, remember that two formulas that are identical on paper can behave wildly differently on a computer. And finally, know the limits of your tools. Your first-order compass, the gradient, is vital, but sometimes you need that second-order topographical map, the Hessian, to really understand the curvature and the condition number of the terrain you're trying to cross.
Ultimately, what all this really shows us is that building great deep learning systems isn't just about fancy high-level theory. It is just as much about smart, robust, and sometimes gritty numerical engineering. It's about designing systems that don't just work in theory, but work in practice on real hardware.
And all this leaves us with one final lingering question. We've uncovered two major numerical traps today, but the landscape of computation is full of them. What other invisible, subtle issues are lurking in our code, quietly deciding whether our models succeed or silently fail?